they'll open up their mantle cavity, water will enter, then they'll squeeze it shut, and water will exit, and they can go very, very fast.
So can I ask a question?
Yeah, sure.
Last week, who was saying it, but weren't we saying that it was really costly to do that, and so typically you wanted water to be able to flow continuously in one direction?
It really is, though, flowing continuously. So what would be expensive potentially is if you had water entering and exiting the jet orifice, because then you have to stop any jet flow before you start again. But this is essentially a unidirectional system.
So how is it?
Because the water.
Banking off the.
No, because it's entering here and it's leaving here, so it's going in one direction the whole time.
Oh, okay. But it still has to be redirected.
Not for sure. So what might be better?
It's not really right though. I mean, it's coming in around the opening of the mantle cavity and then being redirected back out in the same direction it came in. So it is changing direction. It's moving in a circular flow pattern.
Yeah.
It is turning around and going back out the opposite way.
Right. But it's not coming in, stopping, and reversing.
Yeah.
I think, or that is not entirely.
Exactly. So
it's
there's
collision mitigation.
Yeah, and essentially, right? You're preserving the momentum of the fluid by having a one-directional system.
Got it.
So anyway, so that's what they do. It doesn't look like there's a very good video of. Sorry, I need to make sure I quit. I always forget to quit this thing. Everyone, look away from your screens. Okay, so here's a good video. Let me see. Octopus camouflage. It's a very, if I can find it. Here we go.
If you're an octopus or a cephalopod, you need to really
blah, blah, blah. Here we go.
Color and texture. There's some algae in the foreground.
So this shows not only the amazing
octopus.
camouflage of.
Isn't that amazing?
And there it
the
goes.
rocker spooked him, so he took off.
So that's him jetting away, right?
The octopus says, "Look, I've been seeing best thing to do is
So-
get as big as I can get."
So anyway, that demonstrates sort of how high performance this can be. It is extremely high accelerations associated with this jetting propulsion. But what's interesting is that these two authors, Gabriel Wemeth, who's now at the University of Southampton, I think, and Michael Trantafilo, I don't know how to pronounce his name, who's at MIT, they sort of came up with this concept of, not only are they jetting, which is sort of a well understood phenomenon, but they're also taking advantage of this other thing. So that's what we're going to talk about today. Okay, so basically the thought experiment here is, let's consider three cases. One is the sort of standard jetting scenario where you have a rocket in space, in this case this spherical rocket, that's just shooting water or whatever out of its back end, and it creates a reaction in the other direction. So to figure out how you would solve for this, basically we have to do a little bit of math. So I'll try to keep this as clear as possible, but if you want to stop me, let me know. And basically the way we solve this case is we know that momentum of the system is conserved. So the rate of change of the momentum of the system is zero. And that momentum consists of both this the mass of the fluid being ejected and the mass of the object as well. And so because momentum is conserved, and because that means that the net force acting on the system is zero, which means that if we have an acceleration, it has to be equal and opposite in both directions. So the acceleration of the fluid or the force acting on the jet has to equal the force acting on the bottom. Okay, so all we need to do now is basically say solve for the momentum of the system, And so we're going to say that there's the mass of the rocket times its velocity plus the mass of the jet times its velocity. So, which we will call this. So it's U minus Uj. So Uj is the relative speed of the jet, and it's going backwards. And it just turns out that putting it in this way simplifies things later on. Okay, so mj in this case is sort of the mass ejected in one tiny instant. So we're looking at sort of one window in time, and we're saying there's a very small change in mass in the jet, and there's a very small change in the mass of the rocket, and we're looking at that infinitesimal change. So keep that in mind. All right, so we can expand this out, and this turns out to be m by the chain rule, m dot r times u plus mr times u dot plus mj dot times u plus mj times u dot. There's going to be a lot of terms, but we'll get rid of them pretty soon. Minus mj dot uj minus mj uj. Okay. Hey guys. Sorry. No worries. Welcome. Glad you could make it. So yeah, we're just working through case A here. This is a rocket in space, and we're just deriving the rocket equation for everyone. So what we know is that there should be a dot there. We know that, is everyone familiar with dot notation? Mm-hmm. So that's the time rate of change of the thing. So we know that the jet speed, let's just assume it's constant, so the time rate of change is 0, right? And because we're dealing with sort of an infinitesimal change in the jet, the mass of the jet we can neglect. So that's going to be 0 as well, all right? But the rate of change of the jetting mass we can't neglect. So this thing needs to be, we need to keep that. But we know that the rate of change of the mass of the rocket and the rate of change of the mass of the jet, or the mass being emitted, are the same and opposite, right? So we know that, let's say that the rate of change of the mass of the jet is negative the rate of change of the mass of the rocket, which we'll just call negative m dot. So the rate of change of the rocket. Okay. So what this means is that 0 again equals m dot u plus. So at this point we're just replacing mr with m dot. We're replacing mj with negative m dot. That's all we're doing. Plus m, so we'll just replace m with mr. Dot minus m dot u plus m dot uj. Okay, so this term here and this term here cancel out, which is really nice. And so, and then if we move this to that side and we keep this on this side, what we get is mv dot, which is our good old friend ma, which is just the force acting on the rocket, is equal to negative m dot uj. And so this is the differential equation for a rocket. There you go. Now you're all rocket scientists, so bingo. So it turns out that if you integrate both sides, we can now solve for the change in speed of the rocket. So this is a measure of performance. If you ever listen to people talking about rockets, they'll always talk about delta V, delta V, delta V. Well, that comes from this equation. That's just the change of velocity of the rocket. And so what we can think about is the delta U, the change in speed, is equal to the jetting speed times the logarithm the natural logarithm of the initial mass divided by the final mass. And so this term is always greater than 0, or greater than 1, I should say, because the final mass of the rocket is going to be smaller than the initial mass, and the logarithm of a thing that's greater than 1 is always greater than 0, right? So what we get is we get a change, a positive change in the velocity, right? Now this is an aside. This really has nothing to do with the rest of the talk, but it's just a cool point that I like to point out, which is that this is a logarithm, right? And so a logarithm you can kind of think of as a quasi-limit of a divergent function. So if you go to infinity, it does eventually go to infinity. So ln of infinity is infinity, but it diverges very, very slowly at the end. And the consequence of this is that if you want to make you can do the calculation. You can say, okay, if I want a delta U of say 10% the speed of light, so I want a rocket that can actually go an appreciable fraction of the speed of light. What is the initial mass of the rocket, assuming like 20 kilometer per second jet stream, and it turns out to be greater than the mass of the universe. So you can never make a rocket that can get an appreciable fraction of the speed of light.
To go what fraction?
Like any appreciable fraction, like 10% of the speed of light. Yeah, it's interesting, but that's an aside. Okay, so this is all well and good, and all this tells us is it gives us a reference point. So this tells us that if we increase the amount of if we increase the change in the mass, so the initial mass is much greater than the final mass, then we can increase the change in speed. And if we increase the jetting speed, we can also do the same, right? So this just tells us the things we can change. And so what we're going to do now is we're going to take this case, which is underwater, and there's going to be additional forces at play. And what we'll find is that it ends up being much worse as you can imagine. Yeah,
If we take it to the hospital right now.
Okay, yeah. All right. But then we'll also add this change in the diameter of the thing. So it will shrink while it's also accelerating, and we'll see what that does.
So the rocket in space, all that boils down to is basically the rocket.
That's right. So there's no energy being dissipated into the fluid. And so if we look at case 2, what we're considering now is that there's energy being dissipated in the fluid, right? So we have this original equation that we started with. What do we have to add to it now? Any ideas? So what are the additional forces acting on this thing? Drag, obviously, right? So we'll add a term on this side, minus Fd. So this is the drag, or I would call is the viscous drag force, or the viscid drag force. But there's actually an additional force that's inviscid. And does anyone know what it is? I'll give you a hint. It's on the board. The added mass, yeah. So this is a weird concept in fluid dynamics, but it kind of makes sense if you take 10 seconds to actually think about it. Which is that if you're accelerating an object in fluid, you also have to accelerate the fluid around it. So there's, as you're pushing on the object, you're also pushing on the fluid, and that costs you a bit of energy, right? So what happens is there's an additional, what we call the added mass. We'll add it on this side, and there's a change in the momentum of that fluid. And so the concept of the added mass is that fluid is accelerated along with the body, so the body feels heavier than it actually is, right? So if you push on this thing, and let's ignore drag for a moment, you'd be like, my goodness, this thing is pretty heavy. And the reason it's heavy is because you're pushing the fluid as well, right? So, and while the fluid in different parts is accelerated at different rates, we can always normalize it to pretend that it's being accelerated at the same rate as the body, and then it feels like an additional mass. So I will just put those notes down here. Okay. Okay, so I have these notes so that we can refer to them later. There we go. And it's not there.
And the added mass is dependent on some of the material properties?
The added mass is dependent on the geometry of the fluid. I mean, of the object being accelerated.
But
So
don't,
on and so forth. And the density.
And the density of the fluid, yeah.
wouldn't certain materials sort of carry a larger boundary area, or boundary surface, or I guess boundary depth of that water than others?
Probably,
Is that not true?
Probably not, because we usually think of the added mass as an inviscid term, which basically ignores viscosity, and what you're talking about is a viscous effect. So it's a bit complicated, but it's a bit about the accounting of fluid forces is the reason why this shouldn't matter. Long story short, if you solve for the forces acting on an object in an inviscid fluid, so there's no viscosity at all, then you come up with this term that's the added mass term, and that's what we think of as solid. Yeah.
Tim was explaining it to me, asked the same question that do the experiment in statics.
Yeah.
So get it,
That's right. Yeah, exactly.
And is it really the mass of the fluid that you're moving, or is it associated with the cost of flow that, the fish swims in the ocean, the ocean doesn't rise and fall.
No.
It's the mass up
Yeah.
and down. You're basically moving that fluid from one place somewhere else and then put it back in that place.
Yeah, you can think of it that way, right? That displacing the fluid involves accelerating it in some sense. Or in particular, actually that's not quite true, because if you move at a constant velocity, there is no added mass term. So accelerating the body means you're also accelerating the fluid in some sense, and that is the term that comes up.
It's essentially just an analogy, because assuming the flow is incompressible, all of the mass, in theory, out to infinity, can be accelerated to some degree, right? So it's just when you sort of integrate all of that with the inviscid assumption, you get something that looks like an extra mass. So
Mhm.
for convenience, you just call it the extra mass.
Yeah.
Interestingly, even though it really is fundamentally an analogy, there's a lot of papers even still being published that describe it as though that's the physical reality.
Yeah.
But it's
Far
not-
out does this affect flow, and that's the flow.
Right. Theoretically to infinity, but if you
Yeah.
integrate all that effect out to infinity, it collapses to a finite.
Well, I think
Define
I
it.
can maybe define it experimentally by a thought experiment. So I have an object in a swimming pool and I apply an impulsive force to that object, and then I observe the change in velocity of that object. So I start with the object being not moving, I apply an impulsive force and I observe the change in velocity of the object. And this force and this change in velocity, the relationship between those two is linear, and that's the inertia of the object. So I think this is just basically what you're looking at. That's how I think of it. So I think that experimentally you can sort of, and then you take the object out of the pool, you weigh it.
It's like an
and you-
effective inertia.
Yeah, exactly, an
Yeah,
effective inertia.
exactly.
In space, which is what you do.
In a swimming pool, yeah.
Yeah, exactly. So this is all sort of equivalent ways of thinking about this. But what it comes down to is that you accelerate the body, you're also
Yeah,
accelerating
exactly.
fluid. And so there's an extra resistance that's in addition to the regular drag that you feel. Okay, so basically we're accelerating the fluid too, and so we need to account for this term as well. We can now, for a sphere, there is an actual equation for this, which honestly doesn't matter that much for this case, but just so that you have sort of reference, and then this will also, if you do end up doing a derivation, this will come up. Is this right? I think that's right. Okay, so where this is the diameter. Oop. Wow, this is bad writing. Diameter. Wow. Okay. Anyway, this is fluid density. Yep. What's up? That makes more sense. I was like, that doesn't seem right. Okay, good. Thank you, Selena. Okay, Cool. So basically, in this case, there's no change in the diameter, right? So added mass is just a constant term, right? So if we were to expand out this, what we would get is m dot a times u plus ma u dot, right? Since there's no change in the added mass, that's 0. And so all we get is this. And so the consequence of this is you have the force on the left side, which is what we care about, right? The force on the rocket, which is equal to the sort of the jetting impulse minus the viscid drag force, and then minus this added mass term. The reason I'm writing this out is just to show you that this is going to be positive, right? Because the rate of change, the rate of change of the mass is negative, right? So that's positive. This is negative, and this is also negative, right? Because the acceleration is positive, u dot is positive. So this is detrimental to what we're trying to accomplish. And it turns out that if you integrate, and now we're solving for, I'm really sorry about that writing here, but if you integrate, you get delta u is equal to uj, and you can sort of expand this out, times the logarithm, oh my goodness.
It never mattered until everyone was watching.
I know, exactly, right? Times the logarithm of mo over mf. Here, let me just do this. Times 3 over 2 plus mo over mf. Okay, so, and actually we can just get rid of this to make it simpler to read. There we go. Okay, cool. So, this is exactly the same as before, except that we have an additional term. So this is going to be less than what we had before. This is really, really bad, and I'm really sorry about that. So let me just see if I can do this. This might help. Okay, so this term here is always less than 1, because the bottom part is always greater than 1, because the final mass has to be smaller than the initial mass. It means that this whole thing is 3 over something greater than 3. Basically what that means is that you're going to get less of a change in velocity than you would before. No surprise, because we have an additional force that's acting as a drag force. And by the way, we've also ignored the implicit drag. Okay, this is all just preamble to get to the cool part, which is what happens if you have a shrinking cylinder. So if you have a shrinking cylinder, we have our original added mass term like before, which is, I'll just write here again. But now it's a function of time, right? So we have the diameter is dependent on time, and in particular what we're going to say is that the rate of change of the diameter is less than 0, so it's negative. So the diameter is getting smaller and smaller and smaller, so it's shrinking, okay? So we have the same thing we had before, which is the force on the rocket is equal to minus muj dot minus fd, so the drag. And then again, we have the added mass term from before, but now we also cannot neglect this additional term. Okay, so because the added mass is changing in time, right? So let's look at what all these terms will do. Okay, so this one is still the jetting velocity. It's not going to change, so this is going to be positive. This is the viscid drag, so this is still negative. This again is that pesky added mass term, that because the acceleration is positive, this term is negative, right? So this is negative. But this term, the rate of change of added mass is positive or negative in this case.
The whole term is positive.
It's, yeah, so think about this. So the added mass term is this guy up here, right? D is, the rate of change of D is negative. So this whole term is going up or going down? The whole term is going down because D is getting smaller. So the added mass is going down, which means that this is actually positive. So this term here looks a whole lot like this term here, which is sort of like saying that in some sense, this squid is taking this added mass and it's using it as an additional propellant. And the mechanics of why this is the case is really strange.
Didn't we already
But-
say that the time rate of added mass was equal to the negative time rate of mass?
No, the time rate of change of the jetting mass is equal to the time rate of change.
Oh, the jetting, okay.
Yeah. So this is the added mass in the fluid.
But it's still the same sign.
Yeah. So this is really weird, right? Because you're accelerating this fluid, and that should create a resistant force. But because that acceleration is changing in time, somehow you get that force back later on, right? Like this is really strange, and I still don't really fully understand it. But the math here doesn't lie unless we make some horrible assumption. And what we'll see later on is that this actually holds up. But we can solve this, right? So just in case you guys end up doing this later, just remember that m, the mass of the spheroid or the sphere is just this equation. So we can relate the mass, all these terms, to D, right? And we'll just neglect the drag force for now. And
Why doesn't that be 1/6? The fourth implied value
was it 1/6? What do you mean?
because that's 4/3 times
That's the entire mass of the sphere, not the added mass.
Right, but it, I mean, if that, doesn't that formula go around the 1/6 high density value? There's 4 of the 20.
Yeah. So this is just the good old 4/3 pi r cubed,
Yeah.
and it's just d over 2.
But he's saying it simplifies to.
Yeah.
That's
Sure.
probably 1/6 and nothing.
Yeah,
This is the displacement.
Okay. So these are two different
Added mass
things.
and mechanics talking about right now, two
Yeah.
different things.
This is the mass of the rocket, and this is the added mass of the fluid. Yeah. Okay. Yes. Glad we cleared that up. So we'll write everything in terms of d, and what we find is that delta u is equal to 2 times the cube root of mo over mf minus 1, which should mean nothing to you. But we can plot this, right? So we can compare how this performs relative to the other cases. And it does this. So we have, this is the original case, so the sphere in space, right? And this is the logarithmic behavior of that. By the way, this is the change in velocity relative to the jetting velocity, right? And this is the mass ratio, so the initial mass divided by the final. So we get that logarithmic behavior in the sphere in space. We get much worse performance in the sphere underwater. But for the shrinking sphere, there's actually a point where it exceeds the performance of the other one. So when the mass ratio is 10 or more, which means that your final mass is less than 10 times your starting mass, the additional thrust you get from shrinking, or what they call the added mass recovery, is greater than the detriment added mass posed to you.
So does that
Yeah. Huh, right?
does that relationship rely on diameter and time? the profile of it?
Yeah, it does, right.
What
So,
profile are you using?
so in this case, we're just thinking about a sphere that's just shrinking.
Linearly? In time?
No. So it doesn't actually depend
No?
on the profile. No, it doesn't.
Assuming a constant jet velocity.
It's assuming a constant jet velocity. Yeah. So I guess it does.
So then the volume shrinks
The-
like if
Yeah,
It's
the
very
volume
square.
will shrink with a very particular thing. So that's true. The jetting velocity is constant in all these cases. But yeah, you can play around with this, and this is what these authors have done in this paper. But what they find is that you do actually end up getting crazy performance. Now, one thing we have neglected here is that drag force, the viscid drag, right? And so there should be a dependence on the velocity you're going, as well as your size, which is going to change in time, as well as hysteresis, right? So what happened before might affect your drag later on. So this is not a very simple thing to solve. So they did it numerically, and in particular, I think. Do you remember if this is the prolate spheroid, or is this just the sphere?
I think that was the sphere, right?
Okay. Anyway, some shape that is shrinking in time, and what they're plotting here is they're plotting drag as a function of some normalized time. So basically, time. I think that the diameter is shrinking at a constant rate in this case, and so at time 0, it's just started shrinking. At time 1, it's finished shrinking. Okay, so that's all. And then these different colors are basically different rates of shrinking that they parameterize with what they call the shape change number, which I won't get into. But basically what this shows is that there's sort of two inviscid predictions, kind of a lower bound and an upper bound on the viscid predictions. This is basically how bad added mass is, and this is how good added mass can be. And it shows that as you increase that rate of shrinking, it becomes closer and closer to that inviscid prediction, and you get much, much higher performance. And so your drag initially turns into a thrust later on. And so this is why they talk about added mass recovery, because it seems like you're dissipating energy into the fluid, but then you're recovering it later on as energy into the body.
So if you think of this from an energetic perspective,
Mhm.
which you presented there,
Yeah.
putting energy into like mass, in the basically moving through the water,
Yeah.
energy from that mass, and then that energy back into it.
Yeah.
So is the squid doing more work? When it's swimming through water, more work to displace that added mass
Yeah.
as a jet,
Mhm.
and the energy to jet that
Yeah.
water. Is it extending additional work to move that added mass that recovers in the end and say, okay, that's why it's going
Yeah.
faster. It did no work in the first place.
Yeah.
It gets that in all that
It-
energy back eventually. It's lost.
It must. It has to do more work. Now, so anyway, what I will say, I'll put an asterisk there, which is that the squid in space is not accelerating as quickly as the squid underwater. But the squid underwater is definitely doing more work.
That's what, it's
Yeah.
not some magical thing.
It's not a
It's-
exactly.
It's not working as hard
Yeah.
in terms of transduction of energy, muscle contraction,
Yeah.
jets. And so in the end, you're just going slower, assuming it's going to want to recover.
Yes, exactly.
How could that be though? If we simply integrate the force over the distance traveled, if the force is the same at the early time, then it just gets better and better. It actually seems like it must be doing less work overall.
No, that's where the asterisk comes in. So I'm comparing the space, the squid in space, to the squid underwater. Right, so energy has to come from somewhere, and where it comes from is the muscular contraction of the squid. Right? Now, what I don't know is what happens to the efficiency as you contract faster and faster. I don't know the answer to that.
I'm also sort of thinking the same thing. The animal is putting energy into the water as it starts.
Mhm.
Some amount of energy. And some of that is showing up as acceleration.
Mhm.
Some of that is showing up in squid space, all of it is showing up as
Yeah,
acceleration.
exactly.
In squid in the water, some of it is showing up as acceleration of mass, and some of it is showing up as moving that added mass.
Yeah,
So-
and some of it is going into heat, basically, mixing the fluid, right? So
But
that,
so is it doing more work on the water that's ejected, or is just less of it showing up in acceleration and some of it is showing up in added mass, but then how do you wind up switch it goes faster? It's the same amount of.
so the idea is that if you're compressing your body, you are putting energy into the fluid, but at some point, some of that energy comes back to you. And I'm not entirely sure how that happens. And the authors of this paper go into lots of detail of, well, what we can see is we can see an enhanced negative pressure on the front end of the squid later in the profile, so that's what creates the thrust. But it doesn't actually really tell you about the mechanism that much, because of course there has to be lower pressure on the front and the back, because that's what force at the water is, right? A differential pressure creates a force that pushes you forward. So
Struggling with the extra
Yeah.
work are done moving that jet.
Yeah.
Moving that massive water to jet. And that's partitioned into acceleration of the animal and on mass, and the end is still in the jet. The best you can do is get that extremely
right, exactly. So you have to partition this carefully, right? So there's work done on the jet to create the propulsion from the jet itself, and then there's this extra work done, which is the atom mass turn. So that's additional. That's additional. No. That's purely from accelerating this body, which means that the fluid is accelerating as well. And this is where like atom mass gets really sort of like magical and and really weird, because like what is the mechanism? Clearly, what has to be happening is you're putting energy into the fluid, and then the fluid is putting energy back into you. That has to be what's happening, right? But how? That's the question, and I don't know. And then the efficiency question is a really good one, right? Because all of this does have to come from muscular work. So even though it looks like it's definitely a higher performance, is the efficiency of that performance actually better? And that I don't know. It could be that it's actually less efficient once you start contracting very quickly.
You
And-
get a higher power as well, right?
Well, you have to get a higher power,
Right.
right, by necessity, because your acceleration is higher.
That's right.
But is the net energy change versus energy put into contracting, is that higher when you come out the best work or not? And I don't know. And I don't know if anyone's looked into that. Do you know, Eric? Yeah. So
Is there any analogy to thinking about like work minimization and collision-based locomotion?
I don't think so. No.
Like an impulse is more efficient than.
Oh, is an impulse more efficient? Probably, yes. Yeah, so if you contract instantaneously, then that has to be the most efficient way.
Yeah.
But then atom mass doesn't even matter, because atom mass won't matter, because by the time you're done, you basically are done accelerating and your velocity is zero, so there's no atom mass.
So the suffragette is not shrinking itself, the adding mass is just going off.
It's blown off. I don't know if it's blown off as heat. I think it's not blown off as heat. It's blown off as additional kinetic energy in the fluid.
But in the fluid, right?
Yeah.
And so it basically is less.
Yeah, eventually it'll become heat. Yeah.
And so by shrinking the air, putting the energy of that added mass back into
Exactly. Yeah. Yeah. Exactly. So at the end of the day, what these guys showed, and these are all numerical simulations, but then they also built a robot later.
Okay,
I know,
this
right?
yes.
Which took advantage of these principles, and they did demonstrate that there's some additional performance characteristics. So you can get enhanced performance. So this might matter for squid that just wants to go as fast as it can possibly go, and needs to jet really quickly and get away from a predator. That's when it might matter. For efficient locomotion, I don't know, and that's another question. And the other thing that those of you familiar with squid should be thinking about is, hang on a second, so they deflate, but then they're also reinflating, right? So they're getting big again. So the atom mass is going to go up again. So how does that work? So does this mean that if you're pumping, can you actually eliminate the ability to recover atom mass? And I'm not entirely sure, but from my very cursory look at the follow-up literature, it seems that the answer is yes, that actually you can take advantage of a resonance of the atom mass, which is another really weird thing that I'm not going to get into, that I don't understand, but it should be possible to actually still take advantage of this if you pump at the right frequency. Yeah, I know. Isn't this weird?
This is black magic.
It is. It's really, I don't know. I find this stuff really, really cool, really fascinating. I think there's a lot we still don't know about it. And in particular, I think the applicability to biology is also very unknown. So, for example, we know that there has to be, for you to take advantage of this effect, you need a mass ratio of greater than 10. Which means that when you start deflating versus when you end deflating, you've lost 90% of your mass. No, is that right? Yeah, 90%. Which I don't think a squid does, right?
That's only to get an advantage over space, though. You're already getting an advantage over the effect without the subtraction. Right, the three curves.
Yeah, that's true.
So
That is true.
yeah.
That is a good point. Yeah,
Yeah,
that is a good point. Yeah, yeah. So that's actually a really good point.
It's not really competing against space.
You're not, yeah, you're not competing against space squids.
I'm sure they would love to look into it.
Yeah, yeah, that's a very good point. Yeah. But have people looked at shape change numbers or like the actual rate of contraction in squid? I don't know. Have they actually compared their acceleration to what you would predict with these models? I don't know. Has that issue of pumping? At what frequency do you have to pump to take advantage of this effect? Do squid actually do that? I don't know, right? Like there's many questions, and then of course the issue of efficiency of this stuff, which probably doesn't matter when you're just trying to escape.
What can they do with the robot? 10 times the mass. What seems doable with the robot?
Yeah, you can do it with the robot.
And did they show? Can they actually show?
If they shoot a robot into space, then
Yes.
I want squid bots in space.
No, they didn't take it to space.
The Vaughn
Sure, that's
it's
in
the best use of the Vaughn comet there is.
Yeah, sure. Yeah, true.
Already grant.
Yeah, sure.
I mean, yeah, just do it in air, right? So it's operates air is the velocities there.
That's true.
It's predictions, but it's
Yeah.
just compare, you're calculating on things acceleration, how would it be.
Take it to one of the
Yes.
massive vacuums.
Yeah, that's true. Yeah, you can do that.
So,
Or even honestly, just
I just
put it on a scale sideways and just measure this.
Yeah,
out.
measure it.
Yeah. And I can't exactly remember what they did when they did that robot paper, but I sent that out to you guys as well. It's in Bioinspiration and Biomechanics. So,
how do you derive MA?
how do you derive MA? You talk to Eric and he does it for you.
Well, as we said, you assume an invisible flow, and for a given shape, what you're solving for is the invisible flow and the energy associated with that. That's why it's geometry dependent, because the kinetic energy of the surrounding flow depends on how the flow has to move around the body. So basically, it would come down to solving the flow equation for your geometry with the boundary condition that well, this is an interesting point. The boundary condition is that nothing is, that the surface that you're looking at is impermeable. The fact that we have a jet, I don't know if it really matters to say. But
Well, you ignore that for first
it might, yeah. So, and then for simple geometry, it's different stuff. So for spheres, for spheroids, for
rotating airfoils.
Yeah. Wings.
That was my master's.
So do you believe this?
Sorry?
So do you believe this method?
Do we believe
I
this?
guess my
Yeah.
question is, you know, there's a bunch of people who know this stuff pretty well sitting around the table, and we're all coming down to, and then magically the added mass turns into velocity.
Yeah.
And you have no idea how it's.
It's been demonstrated, right? So, like numerically, they show that this is an effect that happens. With the robot, they show that there's an added performance beyond what they can measure, or beyond what would be expected if it wasn't shrinking. So it happens. The question for me is it biologically relevant? And I honestly don't know.
That seems like the physics is solid, it's just a matter
Yeah,
of
the physics is
how
solid.
relevant is it in
And
practice.
the physics is solid, though I would say the mechanism is still a bit unknown.
That's what I'm looking at. How do you
Yeah.
get returns back from that added mass?
Yeah.
into
Now, there's one theory, and Eric, correct me if I'm completely wrong on this, which is that you can kind of think about added mass as sort of attached vorticity on the object itself. Or it's related to it. So as the object is accelerating, there's sort of within the boundary layer, there's sort of things that stay attached and sort of get spinning and like, but just stay attached to the actual object. And you can think of that as being where the added mass term originates. No, not really. Not really.
Yeah, I think you're right. I think the mechanism is, or I don't know about the biological side, but just the aerodynamic mechanism, I think is definitely, if we're getting faster speeds, I don't doubt that. I'm a little skeptical of this idea of actually improving efficiency over like long-term locomotion. That seems like you're violating something.
Yeah.
Conservation of energy, like you're. There's a paper I've seen looking at a different way to cast the equation of force for oscillating. They have an added mass term, and the associated energy sums to zero over time. Because added mass comes from a set of linear equations. So it doesn't make sense that we can get back more than put in.
Yeah, of course. Well, it's just
So the only thing where this could work out, I think, is maybe the fact that you actually have drag, so that you are slowing down because of the other forms of drag, so that when you reinflate, you're going slower at the time you're inflating than when you're deflating. So there's a slight net benefit.
Yeah.
But it's only a benefit you get because you have drag that you've already lost something. Right?
Yeah, I could see
So
that.
you can mitigate the drag loss of something. So
Yeah, I'm very interested to read this sort of added mass resonance paper. Have you read it yet?
no, I haven't.
Okay. It's fairly recent, just came out 2 years ago. Yeah. Anyway.
Now, do you remember talk 2 years ago when I was working in this guy about frogs?
Yeah, was it Richard, what's his name?
Yeah.
Yeah, from RBC.
Yeah.
Uh,
and he had this talk about frogs that have a translation of hip joint.
Yeah.
And I had a chat afterwards with him about that. And then one thing that I noticed, that I thought was maybe interesting, is that for sure if you extend your body as a frog,
Yeah.
and your volume is conserved, then you will probably shrink the diameter.
Yeah.
So you think that this has any bearing on that story?
Nope. Zero. Because the added mass term, if we go back, depends on the density of your fluid, right? So, yeah, here's your added mass term, MA equals blah, 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 density. And, yeah, no worries, thanks for coming back. And so the density of air is what, 1,000,000 times smaller than the density of water? Something completely ridiculous. So basically, no, it's not going to matter in air.
Thanks for that.
Is it 1,000? I can't remember.
No, but the frog was swimming.
Oh, the frog was swimming.
Yeah, it's a
Oh,
swimming
okay,
frog.
okay,
Yeah,
interesting.
So he does this
Okay.
during swimming. No, that's why I'm asking. No,
Okay.
sure, during air. It's,
Yeah, so I'm familiar more with his work of jumping frogs, which is why I was confused.
Oh,
Yeah,
okay.
it might.
No, and actually,
No.
and the particular part about the frog is that this is a aqueous
Yeah.
species, so it's only besides in water.
Yeah. So it might matter. It might matter. And then the other way, the other place where this might matter too, is actually when you have even just swimming like this, like doing kind of the breaststroke sort of style of swimming, where you have a very large area and then a very small area. And added mass is very tightly associated with your frontal area. So if you're traveling forward,
Yeah,
it's the total area that you're taking up. And so as you're expanding and contracting, there should be this change in your area. And so that there might be an effect there that hasn't been appreciated before.
As well as change in drag.
There's also change in drag, yes. And that's what makes this sort of analysis very complicated, is because these things are...
But that's the sort of thing that the kinesiologist is more so thinking of than
Yeah.
adding mass.
Exactly. Yeah. I can also send out all these notes later, guys, if you care. Yeah, so there's that. The other thing I've been thinking about, although I don't know if this matters, is in porpoising as well. So if you have a thing that's jumping up and down, yeah,
Okay, cool.
porpoising. Yeah, porpoise is porpoise.
What is your purpose
What's
of
the
bringing this
purpose
up
of a
right now?
porpoise?
Exactly.
So because you're basically you're essentially shrinking when you leave the water, right? Because you have a certain amount of your body is underwater, and then it gets smaller and smaller than you've left. And so there's a change in the added mass there as well. And whether that there's a similar effect there is, I can think about it. I don't know. Yeah, you get free surface effects, but anyway.
You do have an additional benefit, but I think related to what you're saying, that this analysis is just for a sphere, so keeping the same shape, which is
Mhm.
a similar shape shrinking.
Mhm.
But if, for the same volume even, if you just rearrange the geometry
Mhm.
to be forward,
Yeah.
then you would also decrease the added mass,
You
and
would.
therefore get a even more,
Yeah.
even
Yeah.
better advantage than what you're saying.
Yeah, and a squid is very definitely not spherical.
Yes, definitely.
It's probably, I'm assuming it's getting even less spherical when it contracts, so it's probably, it's like getting even more elongated.
Not necessarily, it depends where they are in the jet cycle, they kind of bunch up and then elongate.
Yeah.
Okay.
Yeah, but the other interesting thing though, which I think is relevant to this effect, is when squid and octopi jet as an escape maneuver, they first hyperinflate. So they do end up being like extra big, and then they jet, right?
Which means they're probably trying to, they may be maximizing that effect.
They may be maximizing that effect. Now, people have pointed also to sort of an elastic storage effect, which is definitely is a possible other mechanism. But it seems like you can get two things for the price of one, right? If you hyperinflate, you get that benefit of that power amplification from the elastic storage, but you also get an additional boost from this added mass effect. Potentially, you'd have to look because you do get an additional cost early from the extra size, but you might get an additional benefit later. So it'd be interesting to look into that as well.
You think if you do that too much, so it'll take too long, if your purpose is to jet away as quick as possible?
Yep. So there's a trade-off there.
It's like full on attack plan, so.
Yeah.
They're fast though.
They are fast. Very fast. So. Anyway, so that is the weird black magic of added mass recovery.